Seems so.
Okay. Then we continue with the second talk by Mariana Carrillo González, telling us all about bounding effective field theories from flat space to cosmological spacetimes. Stage is yours.
Thank you. Well, first of all, thanks to the organizers for organizing this very nice program and also to invite me to give this talk. So I guess I'm going to apologize first because this is not going to include directly any quantum gravity, but it's going to be techniques that I will say that should guide you for what is the effective field theory that should arise from a quantum gravity. So the idea is basically telling you what are going to be the values of the Wilson coefficients on any effective field theory that you should consider to be a reasonable physical effective field theory. So we already talked a lot about effective field theories in the previous talk, but let me just briefly remind you what is our thought of what we think about effective field theories. Basically, we're going to have a cutoff scale here called lambda. Above this energy scale, we don't know what our theory is. We have ignorance, there's the UV, and I'm going to be just assuming that I don't know anything about it. Below this scale, we can have an effective field theory, and we can describe this with many operators. You just decide what fields are going to be your content, what symmetries you want, and then you're going to have an infinite series of these operators with some Wilson coefficients. So for example, as the simplest case is a shift symmetric scalar. That is what I'm showing you here. And the next order, like higher derivative corrections, will look something like this. So the question here is, what are the values of these coefficients in front of these operators? From effective field theory's point of view, there's no a priori value for this, but we know that if you just take any number that you want and put it in there, it can lead to unphysical observations. Another reason why this is important is because if you actually want to go and work with data and you want to do like inference of cosmological parameters and you do estimations, you have to put priors. You have to give a value of these coefficients and actually measure and see what you obtain. And depending on what priors you give, you can get very different results on the estimations of these parameters. So what I'm showing you here is an example for modified gravity theories, but it's not really important what any of these values mean. But what I want you to focus on is that if you don't put any priors, not put anything that we know from theory that you should expect, you will get the orange here, for example. But if you start putting more theoretical priors of what you will expect an effective field theory, a reasonable physical effective field theory will have, it can start changing very drastically to these blobs over here. So the experimentalists will tell you different values that you will observe depending on what priors you put. So you should be very careful, and it is something important. So now the question is how to put these priors. And we have many different ways of doing this, starting from, let's say, a lot of assumptions to I'm going to weaken my assumptions as much as possible. So one of the first ones is to decide what is the UV. Maybe you can decide that this is string theory and get some strong-like conjectures. Maybe you can decide that it's some other, your favorite quantum gravity theory. And once you have those conjectures, you can start putting some bounds and what you can expect of the values of these Wilson coefficients. This is one of the strongest cases because you assume that you know your UV. You can weaken this, and now you say that you want certain properties of your UV theory, not specifically which UV theory you want it to be. So this goes under the name of positivity bounds. And the idea here is now that you're going to have a UV that is local, unitary, causal, and Lorentz invariant. And all of these properties allow you to write dispersion relations for your amplitudes, because now you're going to know what are the analytic properties of these amplitudes in your complex S-plane, S being the Mandelstam variable. And this allows you to do contour integrals and put bounds on these coefficients. So here I'm showing you what is the standard positivity bound described very long ago. And the idea is basically to look at your scattering amplitude in what is called the forward limit, so taking the Mandelstam variable t to 0, so theta, the angle of scattering 0. And in this case, you can look at this integral, this contour integral over here. And now you can do the contour in the IR, and what you will get will be simply the second derivative of your amplitude evaluated at t equals 0. But you can also deform this because we know the analytic properties of our amplitude. When we know where are the branch cuts, we know that it's bounded, so the contours at infinity can vanish. So you can do that. Now deform it to the blue contour, and what you will get is what's on the right side. So first things first, you need locality to assume that there's some polynomial boundedness so that the contour at infinity gives you 0. If you have massive particles, this is just given by the Frazard bound. The second thing is that you also need causality. So you actually can relate the analytic properties of the upper and lower half plane. And then you need Lorentz invariance or crossing symmetry. So you can relate also these integrals in these two branch cuts. And what you end up getting is just the integrals over these branch cuts that give you just imaginary part of the amplitude related to the cross section, so it's positive. So all of these properties together give you one of the simplest so-called positivity bounds, that is that the second derivative of the scattering amplitude with respect to the Mandelstam variable S has to be positive. This has been understood for a long time, and this can put bounds on your Wilson coefficients if you have something that goes like S squared in your amplitude. But again, we're doing several assumptions. We're assuming all of these properties of our UV theory. So what if we want less assumptions? So this is what I'm going to talk about now. Now, this graph that I'm putting here is not that this is where string theory fits in the theories, but this is the amount of assumptions that you have. The less assumptions will be what I'm going to call infrared causality. If you have positivity bounds, this by default will have infrared causality. If you have a theory that comes from string theory, for example, this will by default satisfy positivity bounds, and it will satisfy infrared causality. So the rest of the talk is going to be explaining to you what is this idea of causality bounds and how to find bounds to these Wilson coefficients, but only looking at the infrared and putting no assumptions on the UV. And basically, if you want to think about this again in terms of scattering, instead of doing a 2-to-2 scattering, that's what you do in positivity bounds, this will be like doing a 1-to-1 scattering, but now in a non-trivial background. From the point of view of positivity bounds, you can add all the higher derivative amplitudes, but positivity bounds only looks at 2-to-2 scattering. So it won't look at higher point or... Yes, but for positivity bounds, people don't really know how to do higher point amplitudes. That's the problem. In this, yeah, because it's more complicated when you don't do 2-to-2 of elastic amplitude scattering. So that's one of the drawbacks of the idea of doing positivity bounds, that you mostly know how to do 2-to-2, but you don't know how to do higher point amplitudes because of the problems of knowing the analyticity in the complex plane. You have more Mandelstam variables. So the idea here with causality bounds will work for any scattering. And in the 2-to-2, well, sorry, in the 1-to-1 scattering and non-trivial backgrounds, you can actually have encoded what will be the endpoint scattering in the trivial background. So in a sense, causality bounds help you to constrain those bounds that you can't from positivity bounds. So now let's look at different ideas of what we think about causality. There's the classic idea of just having microcausality, which is having that your operators, your local operators, to commute outside of your light cone. This one in turn also implies that your retarded Green's function will also vanish if you're outside of your light cone. And here what I'm going to use is more slightly more rough idea of what causality is, but basically encoding what is the support of the retarded Green function. So I'm going to be considering local propagation of degrees of freedom around non-trivial backgrounds. And by looking at this propagation and looking at observables, I'm going to measure what is a causal propagation and what is a causal propagation. And this will lead to what are bounds on Wilson coefficients, because different numbers for these coefficients will give you causal or a causal propagation. So these are ideas that were developed a few years ago by Claudio de Ram and Andrew Tolley, but they were just bounding the leading order Wilson coefficient because, as you would expect in an effective field theory, higher and higher orders are suppressed from the EFT. So what I will show you today is how can you actually get bounds on these higher order Wilson coefficients that are naively suppressed. I'm always going to be working with an EFT description. So at low frequencies, this is why I'm calling it infrared causality. And this is going to be diagnosed by looking at the time delay that basically encodes the support outside of the light cone of the Green's function, which is of course, if we work just in flat space, something that is a well-defined observable in terms of the S matrix like this. And the idea, again, is just going to be, we're going to have a localized background. We're going to send a field. We're going to see its perturbations that are going to have a modified propagation due to this localized background. And the modified propagation is with respect to, let's say, a particle like a minimally coupled photon that moves around this background with just the speed of light. So let's imagine now you have a generic field here. Again, I'm writing phi as a scalar, but you can think of this for any spin field. And if you write these equations of motion and you perturb around it around a non-trivial background, you will see that they get a modified light cone. So this is just very standard. So if I call my perturbation phi, they're going to have now a modified light cone that depends on the background that I'm calling phi bar. In principle, the first thing that you will think is that if I have this modified light cone and I look at the speed of sound and that this light cone is larger than the light cone that we see for a photon, then we immediately have a causality. So what I'm going to tell you is that that's not the case. So requiring always that you have superluminal speed of sound is too restrictive, because we don't need this restriction at every point in spacetime, but it's an integrated effect. So when you're going to compute the time delay, you're going to see when I show you the explicit formula for this, that this is actually an integrated effect along the spacetime for the propagation of these waves. So what you need for a causality, indeed, to happen is that you do have superluminal propagation, but not just at one point or not just as a small region in spacetime, but for large regions in spacetime. And there's one more thing, and it's the fact that we know there's quantum mechanics, we know there's uncertainty principle, and we know that there are things that we cannot measure. So if you send in a wave with frequency omega, and you actually want to measure a time delay, and this time delay is smaller than this 1 over omega, we know that this is not a resolvable amount. So in fact, our constraint for what is a causal, or in this case, what is causal, is that the time delay should be not too negative. If it's slightly negative of order 1 over omega, that is okay. That doesn't mean that you're propagating faster than light. It's just for a small amount. It's something that is not measurable. That is why you need a causality for large regions, so that it integrates to an amount that you can actually measure. In terms of microcausality, which will be for, well, yeah, yes, right there. For the operators, it's different because I will need to sandwich that inside a state. So I need to define my state that I'm working with and then actually do the expectation value. So I can rephrase it in terms of the retarded Green's function, which will be having support for the retarded Green's function outside of the light cone by an amount that is resolvable. Yeah. Yes, if you want to, because all of what we're going to be working on is in momentum space for the retarded propagator. If you want to know the full support of the propagator, at some point you will have to integrate over whole momenta, which means you need to know the UV. So
I don't know how to call it, but it's sort of soft violation of microcausality, because we certainly cannot use the fact that theory, even though it has a couple, is defined for arbitrary because it's not valid.
yeah, I'm not defining this as a violation of microcausality. I'm defining this, yes.
Valid up to high this scale, I don't know how to phrase it. Very technical.
To translate to microcausality, yes. Okay, so just to clarify again, so here I'm going to be looking at causality in terms of measurements of time delays that tell you how far your Green's function actually has support outside of your standard light cone. And if it's small but negative, so small as 1 over omega, then it's okay because you're not going to be able to measure it, but in principle, you want it to always be positive.
Yes, matrix that you waiting to.
So it's going to depend on the scattering process you're going to look at. So in principle, if you actually want to have a well-defined scattering process, you need a localized background and to actually have proper asymptotic states that you can have defined an S matrix. This is not going to exist throughout all my talk, only some special cases. So there's cases where you can pretty well define the time delay from an S matrix, and there's going to be cases where I'm going to define a time delay just from the existence of a phase shift, but there's no S matrix. Now, what happens when you include gravity? Because of course we know that when you have gravity, you are going to have also an additional time delay just from GR, but just for being on a curved spacetime. So there are two different notions of what causality in terms of the time delay means when you include gravity. They go under the name of asymptotic causality or infrared causality. So the first idea is that your full time delay, now it's going to be your Shapiro time delay plus your EFT corrections. And in principle, you will say, oh, well, I just want this whole time delay to not be too negative. When you choose that, what you're basically doing is a comparison between light cones, and this is a comparison between the light cone of your effective field theory, or like the perturbation that in your effective field theory sees, versus the light cone seen now asymptotically, like if you're in flat space in Scri plus, for example. Now, there's another notion which is called infrared causality and comes from the idea of I do not need to measure everything just at infinity. I can measure causality locally. And locally, the idea will be instead of comparing with the light cones that you see asymptotically, you want to compare to the local light cones that, for example, a minimally coupled photon sees. That will mean that the minimally coupled photon also sees this part, and your comparison now doesn't have to be the whole time delay, but only that the EFT part just satisfies this constraint. So this is actually a stronger bound. Now, there are different arguments for supporting both of them. And again, it's just an idea of what do you think is the correct comparison that gives you a causal propagation. If you want to believe that you can measure it locally, then you will go for this one. If you think that you should measure it asymptotically, you will go for this one. For the rest of the talk, I'm not really going to have dynamical gravity. At some point, I'm going to include cosmological spacetimes. And I will focus on something of this style, but it's not really a Shapiro time delay, but just including the effects of gravity. So let me now introduce, I'm going to tell you about all of these 3 papers, which is a series of papers developing these techniques. The first one, I'm going to focus on a bit more just because it's going to introduce the whole machinery. Then I'll briefly mention the second one, and I'll try to focus for half of the talk on what you do actually when you look at cosmology. So let's start with how to do causality bounds for scalar EFTs. So if you want to test this idea, you want to test it in the simplest example. The simplest example is a shift symmetric scalar. So I'm going to consider this shift symmetric scalar with an effective field theory just with higher derivative terms. I'm going to consider that I mostly have fields with 4 operators because I want to do a comparison to positivity bounds, but in principle, I could bound higher order operators. So I'm going to do only these 3 operators here, which are dimension 8, 10, and 12, and they just have different numbers of derivatives. I'm also going to couple these. It could be breaking the shift symmetry, or I could also do a coupling that doesn't break it, to an external source. This external source, what it's going to do is going to generate a background. So you can imagine there's some masses that actually generate the background for this scalar field phi, and then you want to look at the propagation around this background. And I'm going to neglect back reaction. So the idea is the following. Now, like this simplified case. You have this source that generated a background for your field phi. Now, this generates this 5-bar background, and you want to assume that you have a separation of scales between your background and between your perturbations, so you can actually measure a phase shift properly. This background is also have to be localized, so you can have proper asymptotic states, and in principle, you can define an S matrix. And the simplest case to look at is assuming that your perturbation is just a plane wave. So if I do that, decompose my field in your background perturbation, assume that these are just plane waves, I can just write the equations of motion, look at this dispersion relation, and the speed of sound. Yes, this will be included in this one special case of this. It gives the simplest bound, basically. So this basically gives you an idea of what to expect, because you're going to look at the speed of sound, and so it's going to have different combinations of derivatives of the background, as you can see here. So these G8 are terms that come from the operators here, G10, these operators, again, G12, now 6 derivatives. And the important thing here is that each one of them, so G8, G10, and G12, have different combinations of the derivatives of the background. Now, if I just do the case as Arkady was saying, when the derivative is constant, it's also very easy to see this term over here is just going to be some positive number, which is what Adams et al. Did. Since it's going to be a positive number and it's going to be a constant, you cannot have a speed of sound that is just constant and that it's going to be superluminal. That will definitely integrate to something measurable. You immediately know that you want this number to be positive. Because if it was negative, then it will be superluminal throughout all space, and that will immediately give you a causality. So you don't want that. And so we can just work with this G8 to be set equal to 1 or 0. 0 gives you extra symmetries, which I'm not going to be talking about here today. So just assume G8 is just equal to 1. It's just absorb if you want in your lambda scale for your cutoff. So I'm going to be looking at bounds between these two Wilson coefficients that I call G10 and G12. And now the game is the following. So you know you have an effective field theory, and the leading order term is the one that is more relevant, and these ones are suppressed by the cutoff scales of the EFT. But when you have a background, there's a game that you can play. And this game is that you can increase and play with the derivatives of this background. So you can increase this combination of derivatives and make this term more relevant than the leading order. So you can select a specific background that actually highlights what this contribution of is and makes this contribution smaller. So now you can actually get bounds on this contribution by playing with getting different backgrounds. So the idea here is that your theory should be causal around any background that can be continuously deformed to the trivial background. So by doing that, I'm going to select a lot of different backgrounds, optimize these backgrounds so that I can get the strongest bounds on these coefficients and find the bounds so that they don't lead to a causal propagation, aka a time delay that is negative and resolvable. So the expression for the time delay basically is going to look like that. Again, it's just very schematic. It's going to be an integral over some region of spacetime, and it's going to be the difference between the speed of light and the speed of sound at leading order. And in front of it is going to have the scales of the background over the scales of the perturbation. So we're going to work in the WKB regime, as I said a bit earlier, because we need a separation of scales to actually have a well-defined phase shift and to be able to compute a time delay. So this over here will be large, but by the EFT, we know also that these terms over here will be small. We just have small deviations from the speed of sound from the EFT terms. So to actually have a causality is going to be a competition between the regimes of validity of the EFT and the WKB regime, so that you can actually get something smaller, larger than 1. So in a second, I will show you explicitly how that works. So let's do again the simplest example, which is now radial background. So what you're going to do is just classic perturbation theory, just expand, if you want your Lagrangian, to second order, get the equations of motion for the perturbation. You can basically do your expansion into spherical harmonics, just look at the radial perturbation. And it's going to look like a Schrodinger-like equation that looks like this. Here, R0 are the scales of the background. Omega are the frequencies of the wave of your perturbation. And there's going to be a term that has an effective potential and your speed of sound. Once you have this in this form of a Schrodinger-like equation, you're basically just going to do your standard quantum mechanics, find a phase shift using the WKB approximation. And this is exactly what I was showing you before. It has the scales of the background over the scales of the perturbation, which is this. And at leading order is the difference between the speed of sound. From this, you can just do a derivative over the frequencies and you can get your time delay. Now, to clarify again, you have to stay within the regime of validity of the EFT and the WKB regime. So you need these omega are not scales to be very large, but you also need these kind of operators to be suppressed from the EFT, which means in terms of the dimensionless scales that I introduced before here. So this phi0 is just the amplitude of the background, and R0 again is the scale of the background. These have to be of order epsilon, just small numbers so that the EFT is under control. So you have to be careful that you're working where the EFT is under control, where the WKB regime is valid, so you can have actually a well-defined phase shift and a well-defined time delay that you can measure. And that means that you have a bound on the energies that you're working with. So they have to be large for the WKB, but small for the EFT regime. But let's just go to the results. And again, so here what I'm showing you is the bounds between those operators G10 and G12. From positivity bounds, this you can find from 2 to 2 scattering. From causality, everything I've told you how to solve this with the WKB is basically equivalent to computing a 1-to-1 scattering amplitude on a non-trivial background. And we get that the causality bounds reproduce very nicely most of the positivity bounds. We just have an issue of not being able to reproduce the top part, but it was just some technical issues with going to very high orders in the WKB expansion. But otherwise, it seems like causality bounds indeed reproduce what you will expect from positivity bounds. So this is a technique that could be useful to avoid using all the assumptions from positivity bounds and just use infrared assumptions. So I'm going to go now just quickly to show you that it works also for fields that are not scalars. So the scattering amplitudes now will be for an effective field theory of a photon. I'm not going to show you the Lagrangian because it's horrendous and it's easier to just see the amplitudes. Now you have operators of dimension 8, 10, and 12, just as before, which means these are f to the 4, now 2 derivatives on n to the 4, or 4 derivatives on f to the 4. And each one here with its corresponding contributions to the amplitudes. And of course, now you have different helicities, so you have different combinations of the amplitudes and the helicities. But the game, again, is going to be the same. For positivity bounds, you can do, again, just look at these amplitudes and do dispersion relations and find positivity bounds. From causality, you can look at propagation around a non-trivial background. In this case, it can be just an electric background. So you can imagine you just put some electric charges and do a propagation around those electric charges and see when you get a causalities from the coefficients of these higher order operators. Now you can again put a radial background, but you're going to have 2 modes. You're going to have an odd and even mode, again, because this is a photon, but the idea is the same. You get Schrodinger-like equations. You get 2 different time delays, and now you want the bound from both time delays. So just to show you really quickly, this you can get a bit more out of it. I haven't told you exactly what these Wilson coefficients are, but they're going to be dimension 10. And for causality, we have these solid lines over here. And from analytic positivity bounds, we get these regimes. So we can combine both now, positivity and causality in this case, and get a very strong bound on our Wilson coefficients. So this can be very useful. Also, the fact that they are not exactly the same, just as in the scalar, is just because both causality bounds and positivity bounds are harder to do for a spin-1 field. So I'm comparing here positivity bounds that are analytic, not the full numerical versions that have been computed in other cases, and causality bounds as strong as we were able to get. But it doesn't mean that these are in conflict with each other. This just means they're probing different regions of the parameter space. So it is useful to do both analytic techniques at the same time and get stronger bounds without having to use heavy numerics. So let's go now to the actual part of how to apply this to cosmology. And to do this, I'm going to go back to a brief review of how we're thinking about causality. So let's just go back to the beginning of what I was talking about of propagation. Let's imagine now we have a wave packet. So we have this wave packet. It goes around some non-trivial background, comes out, and then you do a measurement. What we've been doing so far is a case where you have energies conserved, in which you do a measurement at a fixed radius. And when you do this measurement at a fixed radius, the correct quantity, of course, was the time delay that we were doing. But once you're going to move to cosmology, this is not going to be the case. You don't have energies conserved anymore. Now what you have is a spatial momentum being conserved. And now the correct quantity, instead of time delay, is going to be a spatial shift. That is defined analogously. If you can actually do the computation, you can grab a wave packet, take it out, and see that what you get is that there's now, for the center of the wave packet, a spatial delay given by the k derivative now of your phase shift. This is the correct measurement when you do a fixed time slice and you actually have conserved k. So let's think a bit more about it. So when you do what I was doing before, you basically are taking your spacetime, doing an R slicing. And if you want, you're measuring at some point far from where your scatterer is. But around all of this part of your spacetime, you actually still have radial symmetry. So you can think that the time delay that you measured here actually corresponds to the time delay right at the boundary of your scatterer. So what it's telling you basically is that if it's negative, then the wave left the scatterer before it even arrived to it, which is a causal. The same idea follows if you do it now with a time slicing. So now imagine you grab your spacetime, instead of radial slicing, you do a time slicing, you fix at a fixed time slice away from your scatterer. And again, on this region, you can actually do a time translation and interpret this phase, this spatial shift that you measured over here, interpret it as measuring right at the boundary of your scatterer. And the interpretation is the same. Now your wave, if this is positive, basically your wave is leaving the scatterer before it arrived to it. So this is the idea of how to apply this to cosmology. Instead of looking at time delays, you're going to be looking at spatial delays. Now let's focus on an FRW spacetime. So what you have is basically this spacetime here. I'm going to be working on conformal coordinates. And instead of measuring, of course, just any spatial delay, you're going to be looking at the physical distances. So in principle, you want to look at this multiplied by the scale factor. But also you want to compare to wavelengths that are physical, which means that there's going to be another scale factor here for this inverse wavelength that you get. So at the end of the day, it's very similar to what we had before, but now you have an integral over time and the difference between the speed of sound that you have in the EFT and the speed of sound of FRW. So if you send your cutoff to infinity and you just have what your speed of sound would be without the EFT. So here, notice, I mean, this is important that you don't put the flat space part because you have gravity now, you have a curved background, so you have a deformation from the speed of sound just from curvature. If you want to look at this in a different way, you can think of just having a dispersion relation for your theory, and you can rewrite this in terms of your dispersion relation and conformal time. So this integral over this derivative of Q, which I forgot to define, but Q is just this physical momentum. K over A will be the physical momentum, and 1 over H is the Hubble scale. So you just have a derivative of Q of your dispersion relation should be smaller than K times the difference in time that you measure through. So this is very analogous to what you do with time delays, but again, you're just doing spatial shifts, and now you just want them to not move faster than the light comes in by FRW. Now, to give an explicit example, we can do this in the CIDR. So we can imagine that we work in the Poincaré patch. You start with a Bunch-Davis vacuum, you evolve, and at some point there's going to be some background, there's just going to be a blip in time, then it disappears, and you're going to measure at a fixed time slice. And now you're going to measure at a fixed time slice that is smaller than 1 over K, which means that your modes have not exited the horizon. this is necessary to have a WKB approximation within cosmology. So you can only evolve to so far. But that's okay. You can just do that, measure at that time slice, and check what will be your spatial shift. Again, we're going to test this with the simplest scenario, which is just the shift symmetric scalar. Now the external source is going to be time dependent. As I said, it's just going to give rise to a background that's a small blip in time. You pass it, and then you should be able to define your phase shift and a spatial delay. And here I'm going to include a operator with 6 derivatives just because I'm actually, 6 fields because I'm actually able to test this, and it's going to be an interesting result. The WKB and EFT approximations look very similar to the previous case, but now with the scales that are time dependent. To get rid of a bit of the time dependence and make things easier, I'm going to choose a background that's localized near a conformal time that's 1 over h. So basically my background looks like a blip in time like this around tau equal to minus 1 over h. This WKB just means, again, as I said, that your time slice has to be most inside the horizon. The EFT now is operators with covariant derivatives because you're in FRW. And again, you just do an optimization procedure. You can select your background, you can select different backgrounds so they can test different operators in the EFT and get the strongest bounce. So let me just show you the results. So this is the result comparing what you get in cosmology versus what you get in positivity bounds. Positivity bounds, you should remember, only apply to flat space. So it is okay if they're entirely different. So these were the operators that we had before, the G10, so 6 derivatives, and the G12, which is 8 derivatives. The bounds are not as strong as the ones from flat space, and they're only one-sided. This is likely also just because I took a simple time-dependent profile. I could have taken something that is more complicated and might have given stronger bounds, but it's not very clear how to define a spatial shift in those cases. But perhaps an interesting one is the bounds on higher order operators, like with 6 scalars and 6 derivatives. It gives a very strong bound that looks like this. And in flat space, in principle, you're not able to do this except if you make many extra assumptions. The extra assumptions are that you only have that operator. So if you, instead of having a whole EFT, you consider that you only have an operator with these derivatives, and that's your whole theory, you could put this bound. In principle, I would say this is not correct because we know it's an effective field theory. You should take into account all the other operators and their contributions. And once you do, you should get different results. And indeed, this is what you get in cosmology, that is not such a tight bound. Not that I have found.
That I mean, we met that is the case. Then what is the philosophy of applying these bounds? I mean, would you be happy with the theory that satisfies these bounds on Minkowski, but then you never know if there is some curved background out there which gives you tighter constraints.
Yes, so this is going to be a problem of what's your effective field theory, because there are effective field theories that are specifically defined to only work in flat space. There are some effective field theories specifically defined to work only in cosmological spacetimes. But if you are working, let's say, instead of bottom up, you actually have a UV theory and you get your effective field theory, you will expect that this effective field theory, if it's covariant, is valid in all curved spacetimes that are physical. So that one should just be satisfied in the bounds in all of them. But there are cases of other kinds of effective field theories, like EFT of inflation, or some that I'm going to show you next, that are not defined in flat space. So there's just no way of doing anything there. They just satisfy the bounds on their curved space, and that's it. Yes?
Go to the standard conflict, you have some background like field or so on. you're not talking about a closed system. We have an open system. And I don't know how you can address this in the theory where you have gravitational effect, which naively I would say serves as the same thing.
It should, yes.
Which means that if you study something like this, the first background. But I mean, always take the cheap exit and say,
Yes. Yes, I mean, if you only care about causality and don't start looking at unitarity, this applies just as well. And the reason is because I'm assuming that the background is not dynamical, it's just there's no back reaction. I just checked that.
that's
So, but if you think about unitarity, then it gets messy. I mean, there's some people that, I mean, you could try to define something like an amplitude around core backgrounds, and as has been mentioned, there's some people that have done things like that. But to actually look at the unitarity properties of any analyticity properties of that, it's very hard. So I don't know if people have looked at that. Yeah. Okay, so the next case is actually the effective field theories that are not defined on flat backgrounds. So this is go under the name of Galileans. There are some Galilean theories. They're shift symmetric scalars. They have this symmetry over here. But besides just having a symmetry under just a constant shift, they also have a symmetry under a space-time dependent shift that looks like that. They are interesting for cosmology because they can be useful for early universe physics or for dark energy, and they also arise very naturally in many modified gravity theories. So it will be interesting to see if I actually put these theories in a core background, and there are generalizations to define them in these core backgrounds, if they are bounds for them that people can use when they actually go and test them. And there are two generalizations for these theories that go under the names of covariant Galileans. These ones are special because they keep second-order differential equations, even though you have higher-order derivatives. They have a weakly broken Galilean symmetry. So the symmetry that I told you arises in flat space is just weakly broken in this case, and they can be defined around any core background. There's another case, which is a generalization purely for de Sitter and has a different type of shift symmetry, and also includes a symmetry breaking potential that's still symmetric under this. So now you can actually put bounds on these theories. They're nonlinear bounds. They are quite strong and they're very nice. This is an example for the de Sitter Galilean. Basically, this is the F8 is a cubic interaction with 4 derivatives, and this is a quartic interaction with 6 derivatives. So you can see the blue area will be the one that's causal, and anything in here would be a causal. This can also help to distinguish theories between these generalizations of Galileans because I'm not showing it here, but the covariant case, actually the bound goes the other way, so it's going to be a parabola to the other side. And another important check is that you wouldn't expect that any potential terms give you a causality. Potential terms do not change the causal structure, only the higher derivative terms. So in these theories that actually have a potential, you can check if the potential that has some effective mass can actually change what you see. And indeed, it will give rise to a spatial delay, but this spatial delay is always unresolvable as expected, so it doesn't change anything of causality properties. So basically, as a summary of what I've been telling you, there's a different method for putting bounds on Wilson coefficients besides assuming properties of the UV, which is the infrared causality. There's no need for the UV assumptions. It can be complementary to positivity bounds in some cases, like with the photon EFTs. So it can be useful to apply this approach in flat space in combination with analytic methods to positivity bounds instead of doing heavy numerics. It can also test beyond the 4 field operators. If you want a covariant theory and you actually just look at the one-to-one scattering, it will test beyond these 4 field operators. And it can be applied to curve backgrounds, including cosmological backgrounds. So some of the future directions to do with this, of course, is to test higher dimensional gravitational operators, which is what most people will be interested here. Of course, we're doing this step by step since the scalar field easier than you do the spin 1, then we can start doing the spin 2 case. But it's also interesting to see how these bounds go to theories that have spontaneous symmetry breakings, for example, from Lorentz symmetry, like the EFT of inflation. And especially because in this case, now you have a theory that's only an effective field theory around cosmological backgrounds. And these theories are usually modified in certain ways to give abundance of primordial black holes in weird ways with these Wilson coefficients. So this can tell you if these phenomenological models that people are giving are reasonable or not. So that will be it. Thank you.
Thanks a lot, also for staying perfectly on time. So it's some time for questions. Yes.
About effective by quantum field theory, leading large distance corrections would not even be local if you had massless particles going around loops, or even if you're interested in scales very much higher than the mass of the quanta that's going around in the loop. For example, the thing that causes the QED charge to run would look roughly like F logarithm box F. It seems to me like, well, do you have ways of analyzing such operators? You're analyzing just local powers of derivatives, if I understand it correctly.
Yes. What could be the cutoff in such theory if you have all logs?
Mass of the electron, like box over mass of electron.
Yes, the logic here is massless particles.
Yeah.
People what?
All massless particles are not supposed to be integrated out.
Then just have a massive quanta and look at the
Well, if it's a
look at
massive, you
scale.
can expand them like
Look
Yeah.
at a scale above the mass of the particle, far above the mass of the particle.
if it's effective.
Then you can do a series expansion.
I mean, the term you were alluding to concerning the electrodynamics is actually f squared times log f squared plus n to the power 4 over n to the power 4, where n is the mass of the
Well, there should be a term that looks just like F log box F. That's the thing that makes the
yeah, but you have to
QED.
accommodate the fact that, of course, you have to accommodate the fact that there's an electron mass, and then you have box plus
Mass squared.
Right, but if I'm looking at a scale above the mass of the electron, then that's essentially just logarithm.
yeah, what I'm saying is that these logarithmic corrections are usually included in effective field. So in that sense, there is some non-locality already in.
Well, only when you expand out in powers of order of the mass. Okay, so you're just saying you're not going to do it. But that's the answer to my question, right? You're just not going to, you're by fiat not going to examine it.
I mean, in principle, if what you want is just to keep, I could do a series expansion and just do it with series expansion. But if you just want to keep, it's like the infinite terms in the series expansion.
Then massless particles, your by fiat is not going to include that. For example, in gravity, the leading infrared correction in gravity is not R squared, but R log box R. And it really is log box R with no mass there. There really is no expansion, and you're just by fiat not going to include that, right? That seems to be what you all were saying.
No. I would say logarithmic corrections. Now I'm asking myself, theories you consider logarithmic corrections.
What I have considered so far is just power laws. But in principle, I don't see why you wouldn't be able to include that. I mean, it's just a principle of doing dispersion relations and. For positivity bounds, no. No, for positivity bounds, no. I'm not saying for positivity bounds because that's going to change the analytic structure. That's out of the business. But if all I want to see is propagation around the background of this effective field theory, I can just construct the equation of motion and look at its dispersion relation. It doesn't matter if it has a logarithm or not. I don't see why that will change anything.
They have to be consistent.
Because it's lurking along the background, but it's
Well, I wouldn't call these UV bounds. Well, that's assumptions of weak coupling too that you can put in your theory, I guess. But for the for the photons, for example.
I mean, the standard correction is the log momentum squared plus m squared.
Mhm.
This I can expand.
Yes, and perhaps it's important to clarify there's two techniques here to put the bounds. There's the positivity bounds and then there's the causality bounds. And the positivity bounds will definitely get affected by the logs because it changes the analytic structure of the amplitudes. The causality bounds is simpler in a sense because all you're looking at is dispersion relations. So
Different issue. You mentioned scalar corrections in cosmology that involve derivatives,
Yes.
shift symmetric things. I would have called those quintessence models.
Sure.
It's quite an active field in cosmology. Are you able to put any bounds on quintessence models that we cosmologists thought were okay that you can eliminate? And follow up to that, what goes wrong in those ones that we thought okay that you can eliminate? So for example, suppose something violates one of the bounds. What happens? Does the universe just decay, or what goes on?
That's a pretty good question. I will have to compare the bounds that I have with the literature. I don't know exactly because most of the quintessence ones, would you be thinking of just P of X theories of
Taking the regular kinetic operator,
Yeah.
instead of having it be normalized to one, have it be K of d mu phi. So it's now a nonlinear function of the regular kinetic operator. You can get inflation in those kinds of models.
Yeah, the ones that add a function here, which yeah.
Well, actually,
this one is just like in flat space. It just has to be positive, and I think that's very well known for a while.
So what happens if it's not?
This is basically similar to this. Well, I don't know in cosmology if there's anything explicit, but this just gives the standard story from the Adams et al. Paper from a while ago. Yeah, it will give superluminal propagation for very long distances if you pick some specific background.
Yeah. So what happens?
In terms of an observable. I guess that's model specific. If you're using quintessence as a like dark energy model, I don't know exactly what happens if you put that. But just from my point of view as a physical principle, I would not like the perturbations of my field to travel superluminally.
So that is a principle that just can't happen.
Yes, in a phenomenological perspective, I don't know, because it might depend what you're using your model for. If you're using this as an inflationary model or as a dark energy model or as a
Speeds of sound bigger than the speed of light.
I mean, yes, you would get you will get that for sure. But I guess the
If it happened in the early universe, it didn't happen today.
yes, that's why I'm saying this might be a model dependent context. Like, what are you using your model for? So I'm
mentioned at the beginning that you assume the UV certain principles like locality, causality, and ideal proximity, but what do you have any control of what happens to your positivity bounds around the scalar case if you give up the locality?
So maybe let me back up slide to clarify. So those are the exact assumptions that go under both. So so for the causality bounds, this is exactly all the assumptions we're using. For the positivity bounds, these are all the assumptions we're using. And you want to give up UV locality. So for causality bounds, it doesn't matter. For positivity bounds, this is basically the problem of doing the contour at infinity. So if you have a way of computing that contour, then you can go for it. Otherwise, I don't know what to do with it.
Yep.
So suppose you start with string here.
Mhm. It is expected that they should, yes. They better. So in all the cases that we have partial UV completions or yeah, no. But these ones we've checked with all the UV completions that are known, and the UV completions lie inside or in the corners of the bounds.
Consider scalar and photons, not gravity.
Not yet. For the causality bounds, you can do it as long as you consider, again, a non-dynamical background. So you can take, say, a Schwarzschild background. No, there's no contradiction, but it's only been done for the leading order operators, or if you just put one operator at a time. This whole procedure of actually fine-tuning backgrounds to find more interesting bounds hasn't been done. Yeah, so this is the choice of let me go back to that slide. This is the choice of what you believe it's the correct bound when you include gravity, which is way back here. Yeah, so the paper you're talking about will give rise to uses this idea of asymptotic causality. Usually what we've been doing is using more the idea of infrared causality. And if this is also satisfied, for example, there's the, I think this is also the example they do. You can do QED in a curved background and integrate out the electron. And then you're going to find that these both bounds are satisfied. So I actually should have, if this goes quickly, the explicit expression for that one. So yeah, so that's the, if you do QED in curved backgrounds around a Schwarzschild spacetime, you're gonna get, if you integrate out the electron, for example, a term that looks like this, and it satisfies these bounds. Higher order operators hasn't been done, so. Pure gravity, I think it's also being checked and it's also fine. But one operator, just the first. You can just do one operator at a time. I think they. Which one did they do? Agree and just make it stronger. Let's say, yeah. Make this type of bounds by default agree with the Eidelstein, but they're stronger than those.
Okay, I think time is up, so let's thank our speaker again. And we continue at 11:40